Okay. All right. Susanna is not sure how to find the z-score for a problem on the test. Help explain to her which is the only reasonable guess in the problem below. So the lifespan of a battery is normally distributed with a mean of 2,000 and a standard deviation of 30. Find the z-score that corresponds to the lifespan of 1980 hours, 1,980 hours. Okay. So really quick, just a refresher. We learned this formula last week to find the z-score. Okay, x is whatever the point they give you, mu is the mean, and then standard deviation is 30. So all we're going to do is plug in. And when we do that, we're going to get B. Nothing super crazy. Okay, so today we're going to continue having that conversation about z-score. We're going to use the whole table that we learned last week. So that's what we're going to be working on today. Okay. All right, so it says Zoe scored a 25 on her ACT. Okay. Mike scored an 1150 on his SAT. Which of the two test takers scored better on their respective tests? What proportion of the people scored worse than Zoe and Mike? And assume both tests nearly have a nearly normal distribution. I can't talk. All right, so the first thing that we're going to want to do on this is find the z-score, okay? Because that's going to tell us the number of standard deviations away from the mean. So looking at Zoe, we got a 25. And what is the mean for the ACT? So we have 25 minus the mean, which is going to be 20. And we're going to divide it by that standard deviation, which is going to be 4. So if we take 25 and we subtract 20, and then we divide it by 4, we're going to get 1.25. Now we're going to find the z-score for the SAT. Well, Mike got an 1150. And our mean is 1,000. Our standard deviation is 150. So if we take 1150 minus 1,000 and divide it by 150, we're going to get 1 as our z-score. So looking at this, remember, our z-score tells us how far from the mean this is. So this is 1.25 standard deviations above the mean. This is only 1 standard deviation above the mean. Which one did better? Is 1.25 or 1 higher? 1.25. So Zoe scored better because she scored higher on the standard deviation. The standard deviation was farther away from the mean than Mike's was. Now we're trying to figure out what proportion of people scored worse than Mike and Zoe. But what I want you to do is go into your table on page 19 and 20, on the back of page 19 and 20, and I want you to look at the z-score for 1.25 and 1 and tell me the proportion. So tell me the number that you get. Okay, all right, so we're going to be on page 20. We're looking for 1.25. So on the left-hand side, you're going to go down to where it says 1.2. You're going to go over to where it says 0.05 across that top. So you should get 0.89435. Good morning. Oh, okay. Yeah. Okay, try this one. Go and find 1 to 1.0. So on the left-hand side, you're going to look down where it says 1.0, and you're going to go over 1 column. So when you find that, you should have gotten 0.84134. Again, using the table is probably the hardest part about this. If you don't try it, you're not going to be good at it. Okay? Wow. So suppose you were enrolled in 3 classes, math, science, and music. You just took the first exam in each, and you received a grade of 82 on your math, where your mean grade was 74, standard deviation was 12. You receive a grade of 72 on your science exam, where the mean grade was 65 and the standard deviation was 10. Finally, you receive a grade of 91 on your music exam, where the mean grade was 88 and the standard deviation was 6. Although your highest test score was in music, which was a 91, what class did you score the best relative to the rest of the class? So you know how like you'll take a test and you'll turn to your neighbor and you're like, what'd you get? And like y'all will compare what you got and you'll be like, that test was super hard, that test was super easy. Normal distribution kind of levels the playing field for all classes, if that makes sense. So we're going to look at this first one. We're going to look at math and we're going to find the z-score. So we're doing math first. So we're going to take what you got on the exam minus the mean and then divided by the standard deviation. So we got 82 minus 74 divided by 12. And that's going to give us 0.67. Now looking at the next one, you got science. So we got 72 minus 65, and we're going to divide it by 10. So, say again. 0.67. We're going to do 72 minus 65 divided by 10. And that's going to give us 0.7. Can you figure out the z-score for the last one? That's going to be music. So looking at the music class, we got 91 minus 88, and we're going to divide it by 6. What'd you get? Okay. All right. So just looking at the z-scores, which one is the highest? Which one's got the largest number? 0.67 versus 0.7? Go ahead. 0.5 at the end. That's 0.5. What'd you say, Gravy? 0.67 versus 0.7? Science is higher. Okay. Gotcha. So science would be the highest, even though you made a 72 on it. This is apparently a hard test, right? Because the mean was a 65. Or the kids were just really bad at the test. That's an option too. But 72 minus 67 or 65 divided by 10 gave us 0.7. Okay. So the higher standard deviation was science. So even though in music you made the highest score, in science you did the best relative to the rest of the class. Okay. So on the next one it says, in order to be accepted into a particular program, you must score in the top 5% of the application rubric of those who apply. The mean score is 85 and the standard deviation is 5 points. What score must you get to make it into the program? Okay, so we want top 5%. Your mean is going to be 85 and your standard deviation is going to be 5. This one's a little tricky. Make sure you pay attention on this one. So what you want to do is you want to go into your z-score table and you want to look for, if I'm doing the top 5%, take 5%, turn it to a decimal. Take 5%, turn it into a decimal. 0.05. Okay, but we don't want just 0.05 because that's going to come from that left-hand side. That's going to be the bottom 5%, but we want the top 5%. So we're going to do 1 minus 0.05, and we're going to take 0.95. I'll give you a second to catch up. We're going to look for 0.95 in our table. Okay, so in here, we're looking for 0.95. And the first time that we see it, it happens right here. Now, what's the z-score that's associated with that? Well, that's 1.6. And then if we scroll up and look at the top, 5. Okay, so the z-score that's associated with that is 1.65. Does everybody see how I got that? I went in the table this time, looked for 0.95, then I got 1.65. Okay, so now, going back to what we just had, okay, we've got a z-score of 1.65, and we're trying to find the points. So we're going to use that formula that we've been using. And we're going to say 1.65 equals x minus 85 and divide it by 5. And now we're going to solve for x. So the first thing we're going to do is multiply by 5 on both sides. So if we take 1.65 and we multiply by 5, that's going to give us 8.25. And then when we add 85 to it, we're going to get x equals 93.25. So if you were taking this test, you would have to get a 93.25 at least in order to get it into the program. Quick. Top 5%. That's like your kids who are like smart, right? Okay. And that means that they're probably going to have A's, right? That makes sense, right? Do y'all know what an A plus versus an A minus is? So A minus is a low A, and then an A is a 93 to a 97, and then an A plus is like 97 to 100. 90 to 93. Smart kids. So imagine you were performing an experiment. You decided that you would roll a standard number cube 35 times to collect your data. Draw a dot plot that shows the distribution of values that you might expect for the rolls. So if I rolled a die 35 times, this might be what it looks like. Ta-da! What does that look like? Like the normal curve, right? Like, I mean, when you roll a die, like you normally get like a 3 or 4. You get about 6s. Well, and that might happen. It just kind of depends. This is a possibility. If you rolled a number cube 1 million times and found the mean of all the values, what do you think that mean is going to be? Okay, if you rolled the number cube 1 million times and found the mean for all the values, what do you expect for the mean? It's got to be a number between 1 and 6. What's the mean going to be? Oh, no. 4. Okay, so like halfway between 1 and 6, right? So you could be like 3.5-ish to 4-ish. And the reason why is because those are like the middle numbers, right? We're going to talk about margin of error. So a recent study selected at random 10 groups of 5 people who stream video games online at a certain website and recorded the number of hours per week they streamed video games. Okay, there's the data. What does the sample mean for this estimate? Okay, so what we can do is we can take all these numbers and go into Desmos, type them in, and it'll give us the mean. Okay, we could also sit there and add them up, but I'm not here for that. So when we go into Desmos, we can type out, what's the first number? Guess I'm doing this by myself. Thanks, guys. All right, so 21.2. The next one is going to be 20. The next one is going to be 17.6. Cool. All right, so we're going to get a mean of 17.06. So the mean is going to be 17.06. In order to find the standard deviation, we're going to do the exact same thing, except this time we're going to type STDEV, and that's going to give us a standard deviation of 3.61. Yep. 18.8. Okay, that didn't change the standard deviation. And that just changed to 0.08. Thanks for catching that. Okay. All right, so now we've got to figure out what the margin of error is. On your formula sheet, so on page 19, it's going to give you the formula for margin of error. So I need you to look at your formula sheet. And right here, it's got the formula, which is going to be Z times sigma divided by the square root of n. Okay. The Z that we're going to use is going to be 1.65. Okay, so really quick. When they don't give us any kind of information about confidence level or anything like that, we're going to assume that it's 95%. So at 95%, we're going to have a Z-score of 1.65. This is a number that you're going to have to memorize. Okay, or you could go in and use the table and look that up. So we're going to plug in 1.65 for Z. And our standard deviation was 3.61. And now we need our sample size. Okay, so how many things do we have? We had 10, right? So we're going to divide it by the square root of 10. So we're going to take all of that and we're going to plug it in. We're going to come in here and we're going to say 1.65. We're going to multiply it times 3.61, divide it by the square root of 10. That's going to give us a margin of error of 1.88. We're going to create an interval to estimate the population mean. Okay, so what this is there's a difference between your sample mean versus your population mean. Okay, so when we talk about a sample, we're pulling like a group from the population. When we refer to a population, we're talking about everybody. Okay, so what we're going to do in order to create this interval, we're going to take our mean, which is 17.08, and we're going to add and subtract 1.88. Okay, so we're going to take 17.08 and we're going to add 1.88 to it. And that's going to give us 19.68. And then we're going to take 17.08 and we're going to subtract 1.88. And that's going to give us 15.2. So this is your interval. On your Delta math, it asks you to do this. Okay, so for mean, I got 9,494.2. For standard deviation, I got 2,259.32. For margin of error, remember that z times sigma divided by the square root of n. So that's going to be 1.65 times the standard deviation, which is 2,259.32. And we're going to divide it by the square root of 10. Okay, so we're going to type that in. 1.65 times 2259.32. We're going to divide it by square root of 10. So that margin of error is going to be 1,178.86. And then in order to do our intervals, we're going to take our mean and add and subtract this. So we're going to do 9,494.2, and we're going to add 1,178.86, and then we're going to subtract it. So that's going to give us an interval of 8,315.6 to 10,673.06. Ta-da! Okay, so if we take the mean, which is 105, and we add 21, what number is that going to give me? 126, right? If we take 105 and we subtract 21, we're going to get, we take 105 and we subtract 21 from it. Yeah, I was right. All right, 84. We're looking for numbers that are in between 84 to 126. Is 76 in between there? No. Is 87? Yes. Is C or 105? Yeah. Is 113? And then it's 154. Ta-da! It says mentally evaluate the proportion of chips that are blue. So basically they're asking you to divide. Okay, so if you divided 17 divided by 50, that's going to be roughly 0.34. Okay. And the way you're going to do this in your head without actually having to plug it in is you're going to take whatever this number is and multiply it by 2. The reason why I'm multiplying by 2 is because that makes this 100. So then that gives us our decimal. So what's 28 times 2? $56. So we're going to put 0.56. This next one's a little trickier because we're going to have to multiply by 5 instead this time. So if we take 17 and we multiplied it times 5, we're going to get 85. So we're going to get 0.85. This last one, you probably won't be able to do that really in your head. I mean, you could do it a little bit, but that's going to give you 0.35. On your Delta math, there was a section that was like p hats. That's finding these proportions. All right, so it was determined that 44% of the people would vote for a Republican candidate for president in a city with an error of plus or minus 4%. Find the confidence interval and interpret it in context. So we're going to take this and we're going to turn it to a decimal. That's going to give me what? 0.44, right? And we're going to add and subtract 4%. So when we turn that to a decimal, we're going to get 0.04. So that confidence interval is going to be between 0.4 to 0.48. Okay, so this means that about 40 to 48% would vote Republican. Now, this is really important because when you actually watch like voting happen, you can't just win by 50%. You have to be over 50%. So you have to pay attention to that confidence interval. So in order to win, a candidate must have 50% or more of the total votes. Can you determine if the Republican candidate will win or lose? So really quick, if they are going from 40 to 48%, is he ever going to hit 50%? So if he's from 40 to 48% of the people are going to vote Republican, is this person going to win ever? No, because he's never going to hit 50%. Yep. Because? Yeah, I mean, it's been a while since I've seen it. So. All right, so in an election, the Republican candidate has 48% of the votes with a 3% margin of error. Democratic candidate has 43% of the votes with a 3% margin of error. Determine which candidate will win and explain. So remember, margin of error is you take the mean, you add and subtract the margin of error. I'm going to turn this into a decimal. So we're going to talk about the Republicans first. And we're going to add and subtract 3%. So that's going to give us an interval of 0.45 to 0.51. For the Democrats, they're going to have 0.43. And we're going to add and subtract 0.03. And that's going to give us 0.40 to 0.46. So who's going to win? You have to have 50% or above in order to win. So is either one of these got 50% within their interval? Yes. So that Republican would win this one. Okay. Pause. I made a mistake. Okay, so on this one, he wouldn't necessarily win. There would have to be a runoff, potentially, because watch what would happen. He could hit 51%, but let's say, for instance, he only got 45% of the votes. Well, guess what? He didn't automatically win. This person, however, wouldn't win ever. So there would definitely have to be a runoff or a revote. Yeah, on that first one, there would have to be a runoff or a revote because no one actually hits 50% completely. Let's do the next one together just so I can clarify that. So on the next one, we've got Republican. He's got 51% and we got 3% margin of error. So we got 0.51 and we're going to add and subtract 0.03. So that's going to give us 0.54 for our top number. And then we're going to get 0.48 for the bottom number. For the Democrat, he's going to have 0.43. And add and subtract that margin of error. So that's going to give us 0.4 and 0.46. So now we can say that the Republican would win. 0.4 and then 0.46. This one, we could say that the Republican would win because majority of the time, he's above that 50%. Okay, the Democrat never hit 50%.